So we have to prove this statement here by induction. So here under induction we have 3 steps. So we need to show that it's true for n equals to 1, show that it's we do the inductive hypothesis, which is step number 2. Then we prove that it's also true for n equals to k plus 1 here. So here what we mean here is step 1 here. We need to show that the statement that we have is true for n equals to 1. So meaning that we get this expression that we have on the left hand side that has n in it, and we equate it to the right hand side here. So here we have n open brackets 3 to the power n equal to 2n minus 1, 3 to the power n plus 1 plus 3 here divided by 4 here. So where there's n, we substitute the 1. We're going to have 1 open brackets 3 to the power 1 equal to open brackets here 2 multiplied by 1 minus 1 3 to the power 1 plus 1 plus 3 divided by 4 here. So 3 to the power 3 is just 3 here, or 3 to the power 1 is just 3 here. This will be equal to, so 2 times 1 is 2 minus 1, you just get 1 here. So meaning that if we multiply by anything here, we're simply just going to get whatever we multiply with there. So there we're going to have 3 to the power 2 plus 3 divided by 4. So we have 3 here is equal to 9 plus 3 divided by 4. So 3 there, we're going to have 9 plus 12, get 12 divided by 4. We have 3 is equal to 3 here. So if this is the case here, then this is true for n equal to 1. Okay, so this is step number 1 here. Let's go to step number 2, which is the inductive hypothesis. So step number 2, which is the inductive hypothesis. So here, under the inductive hypothesis, we make an assumption that the statement that we have is true when n is equals to k. So it's true for n equals to k here. So meaning that the only thing that we get to do under this step here is we copy the expression, and then where there's n, we substitute with k there. So here we have 1, 3 here, plus 2, 3 to the power 2, plus, then here we have n. So we substitute the k there, 3 to the power k equal to 2 multiplied by k minus 1, 3 to the power k plus 1 plus 3 divided by 4 here. Okay, so this is the only thing that you get to do under the inductive hypothesis there. Where there's n, you just substitute the k there. Then we go to step number 3. So step number 3 here is that we need to show now here, or we have to show that it's also true for n equals to k plus 1. So meaning that here we're adding a new term now, which is the k plus 1 term there. So meaning that here we copy again the expression the way it is, 1, 3 here, to 3 to the power 2 plus up to the k term. So the k term, we have k, 3 to the power k, plus, since we're talking of the k plus 1 term, meaning that we move a step further from k, going to the right, so that's going to be our k plus 1 term. So here we're going to say k plus 1, okay, so k plus 1, open brackets, 3 to the power k plus 1, close like this, equal to, open brackets, 2 multiplied by k plus 1, minus 1, 3 to the power k plus 1, plus 1, plus 3, divided by 4 here. Alright, now when you look at this step number 3 here, starting from the first term here up until the kth term, this gives us all the terms that we have on the left hand side of the inductive hypothesis here. Meaning that we can just substitute with the right hand side of the inductive hypothesis where we have these terms here. So we're going to have 2k minus 1, 3 to the power k plus 1 plus 3 divided by 4 plus the k plus 1 term now here, which is k plus 1, 3 to the power k plus 1 equal to, so I'll just expand what we have in the brackets there. So here we have 2k, so that's going to be 2 minus 1, we're just going to have plus 1, so 2k plus 1, then we have 3k plus 2 plus 3 divided by 4 here, like that. Alright, so now our goal here is to show that the left hand side is equal to the right hand side, like that there. So with that being the case, we know that this here is just being divided by 1. So we make this here a single fraction there. So everything divided by 4. Then this into this, we just get 1 by that. We're just going to get 3 there. So we have 2k minus 1, 3 to the power k plus 1 plus 3 plus the term that we have now here is 4 open brackets. So because 1 into 4 is 4, so 4 open brackets k plus 1, 3k to the power, or 3 to the power k plus 1 equal to, so what we have this side, or just keep it the way it is for now. So this side we just have 2k plus 1, then 3k plus 2 plus 3 divided by 4, like this here. Now here you notice to say that these two terms here, they have 3 to the power k plus 1, 3 to the power k plus 1. So meaning that there, if we factor it out there, if we get our 3 to the power k plus 1 here, we factor it out, you notice that in the brackets here, this side we're going to have 2k minus 1 plus, then this side we're going to have 4k plus 4 there. So 4k plus 4 plus a 3 this side here. So mean that here I've just expanded 4 times k, we get 4k, 4 times 1 here, we get a 4 like this. Then everything here is being divided by 4. Then this side, I'll keep it the way it is for now. So 2k plus 1, 3 to the power k plus 2 plus 3 divided by 4 here. Okay, so now if we simplify what we have here, you notice that we are going to have 3k plus 1 here, open brackets here, we're going to get 6k plus 1 and negative 1 and 4 there, we're going to get plus 3, so plus 3 here. Then we have everything divided by 4 equal to, then this side I'll copy it again the way it is, 2k plus 1, 3 to the power k plus 2 plus 3 divided by 4 here. Okay, now these two terms that we have inside the brackets here, you notice that 3 is common there, so we can factor out a 3 there. So we're going to have 3 to the power k plus 1 multiplied by the number that will factor out there is 3, open brackets. So here we're going to remain with 2k, like this, plus here we're going to remain with 1. We close here, plus 3, divided by 4. This is being equated to, I'll copy this the way it is, 2k plus 1, 3k plus 2, plus 3, divided by 4 here. Okay, now here you notice to say that these 3 and the base 3 that we have this side are the same. Then this 3 here is being raised to the power 1 here. Now you know that if you have a to the power m multiplied by a to the power n like this here, this is just the same as a to the power m plus n here. We just add the powers there, meaning that here we're simply just going to have 3k plus 1 plus the power of 3 that we have here, which is 1, open brackets, 2k plus 1 like this, plus 3 divided by 4 here is equal to, so copy this the way it is, plus 1, 3 to the power k plus 2 plus 3 divided by 4 here. Then here 1 plus 1 are going to get a 2 there, so that's the same as 3 to the power k plus 2, open brackets, 2k plus 1, so 2k plus 1 plus 3 divided by 4 is equal to 2k plus 1, 3k plus 2 plus 3 divided by 4 here. Now here we can just rewrite this here. We just rearrange it the way it is on the right hand side, this side. So here this is the same as 2k plus 1, then we have 3k, 3 to the power k plus 2 plus 3 divided by 4 is equal to 2k plus 1, 3 to the power k plus 2 plus 3 divided by 4 here. So there we have it. The left hand side here is equal to the right hand side. So if this is the case here, then you can just say, therefore, this is true for n equals to k plus 1. So if this is true for n equals to k plus 1, then what we have here holds under mathematical induction. Like this here. Alright, thank you.